Now we pass on to the derivation of the integrated rate expression for a first order reaction. For a first order reaction. A first order reaction is that reaction in which the rate of the reaction is directly proportional to the concentration of the reactant in the first power. Okay, it is directly proportional to Ca. That is the differential rate expression, that is always the starting point. We can write, consider a reaction that is A giving products. A giving products. Let Ca be the concentration of A. Then we can write the integrated differential rate expression is minus dCA by dt is equal to K into Ca raised to 1. Okay, K into Ca, that is the first order reaction. The reaction in which the rate of disappearance of A is directly proportional to the first power of the concentration of the reactant. Now, let us consider that is A0 be the initial concentration, moles per liter be the initial concentration of A, moles per liter be the initial concentration of the substance A, and let X moles per liter have undergone reaction at the time T. At the time T, okay. Then the amount of the substance A remaining at the time T is A0 minus X. So the amount of A at the time T is A0 minus X. Substituting the Ca in our instantaneous differential equation, that is the practice, that is the technique that we have adopted. Minus dCA by dt is K into Ca. Here it is represent the instantaneous rate equation. Suppose A0 minus X is the instantaneous rate, that is concentration of the reactant at any time T. Then we can replace E as minus d into A0 minus X by dt is equal to K into A0 minus X. Opening this equation, they have minus dA0 by dt, minus minus plus dx by dt is equal to K into A0 minus X. The first differential part is now become 0 because differential of a constant now become equal to 0. Okay. So we can rewrite the equation as, that is, dx by dt that I mentioned. All this equation now comes to the form dx by dt is equal to K into A0 minus X. Okay. A0 minus X. This is the differential form of the rate expression, that is for a first order reaction. Dx by dt is equal to K into A0 minus X before integration. Now we rearrange this equation. Okay, that is dx by, rearrange in such a manner that the concentration term comes on the same side. Dx by A0 minus X is equal to K into dt. K into dt. Now integrate this expression, assuming that K is a constant. So integrating this expression, integral dx by A0 minus X is equal to integral kt or integral K into dt. So integral of 1 by x dx, all of you know, 1 by x ds is log x or ln x. So our answer is, what is this term? That is 1 by, so this ln, the integral 1 by A0 minus X ds is ln A0 minus X, okay, into, you know that 1 by, integral 1 by A0 minus X is minus 1. So we have minus 1 for a0 minus x to integral a0 minus s, that is in here the term, that is minus 1. So we have, that is minus ln a0 minus x is equal to k into integral dt is t plus the integration constant I. Okay? So the integration result is minus ln a0 minus x is equal to kt plus I. Now we have to find out the value of I. You apply the boundary condition, that is when t is equal to 0. When t is equal to 0, x is equal to 0. That is the boundary condition. You see that when t is equal to 0, then x is equal to 0. So we have minus ln a0 minus 0 is equal to k into 0 plus I. Therefore, I now become equal to minus ln a0. So now we got the value of I, that is equal to minus ln a0. Now introduce the value of I into this expression. Now here minus ln a0 minus x is equal to kt plus, okay, minus ln a0. Then you rearrange the equation such that the common term comes to this side here, ln a0 minus ln a0 minus x is equal to kt. So the logarithm term difference is all of you know, is a division. So we have kt is equal to log a0 by a0 minus x. So logarithm of the common term. Okay. Or k is equal to 1 by t ln a0 by a0 minus x. That is equal to, converting this ln into logarithm, that is equal to, that is, we have, that is k is equal to 2.303 by t log a0 by a0 minus x, because all of you know ln is equal to 2.303 log. So when substituting this, we have k, the rate constant k for a first order reaction is equal to 2.303 by t log a0 by a0 minus x. You please look into the equation. This equation is a logarithmic equation. It is give the value of k in terms of the ratio of the two concentration term. Here it is a0 numerator, denominator is also a0 minus x. Both are concentration term. So moles per liter, they cancel each other. So the logarithmic term containing the ratio of the concentration cancel each other. So the unit of k now become time inverse. That is, it contains only unit minutes raised to minus 1 or second inverse, as I have mentioned. So the rate constant k for a first order reaction is, okay, numerical value with a minutes raised to minus 1 or second inverse. There is no concentration term. Okay, so now we have the final equation. Once again, you have to remember it, or you have to write and study well. K is equal to 2.303 by t log a0 by a0 minus